Reverse faults. Reverse faults are faults in which the hanging wall moves up relative to the footwall. In other words, if we consider a section of rock, like we're seeing on this diagram, and let's for now call this the fault plane. So what this is saying is that one block of the rock has moved up and shallower relative to its equivalent on the other side of the fault. So because this part, which is called the hanging wall, that's the part that sits on top of the fault plane, has moved up, in relation to the other part of the same mass of rock that is under the fault plane, we call it a reverse fault, because one originally, because of gravity, everything is supposed to move down, but in this case we see that this component has moved up, climbing on top of itself by sitting on the fault plane. So that is why it's called reverse movement, or reverse deformation, or reverse fault. They actually indicate compressive, or compression of the crust, or shortening of the Earth's crust, and in some case the dip of reverse fault can be as steep as can be steeper than 45 degrees actually. What some authors do is they actually call faults that are lower than 45 degrees in terms of dip angle of the fault plane. They call such faults thrust faults, especially if it's about 15 degrees or lower. But anything above 15, 20, all the way to 45 and above is called a reverse fault. There's also another nomenclature called overthrust, and that's typically where the dip angle of the fault plane is less than 15 degrees. And typically for overthrust, the overlying, that's the hanging wall, can actually move a number of, some significant distance, up to the tune of a kilometer scale, in terms of horizontal or sub-horizontal displacement. There's an area called there's another kind of fault which is called the blind thrust, and that is typically in cases where this fault doesn't make it all the way to the surface. So if it does in such a way that your fault actually comes out, or you can actually see it on the surface, it is no longer a blind thrust. But if you can only see it in the subsurface in such a way that you can only tell that you have fault underneath because of the behavior of the overlying mass of rock, so that the fault doesn't make it all the way to the surface, such kind of fault is called a blind thrust fault. So a bit of hint on identifying reverse fault. First of all, we look out for bumps that take the shape of that are actually asymmetrical in geometry. So we could have one scenario in which case we have a symmetrical bump or anticline. So in this very case, you might be referring to a detachment fold. But in a case where you have some asymmetry to the geometry of the fold, perhaps you might as well actually interpret a fault underneath, because each time you see a bump like this, there is actually something underneath that is driving, that is sitting, that is carrying that bump. So if I see a fault, an anticline that is, asymmetrical in this to the left or to the right, this tells me that there is some push coming from the left, right? And if I see, if the reverse is the case, where I see some asymmetry to the left, that tells me again that the push or the direction of movement is actually from the right to the left. So in this very case, we see an asymmetrical bump which obviously the first message here is that it's sitting on top of a reverse or a thrust fault, and then the second message is that the direction of asymmetry actually tells you the direction of either sediment loading in the basin, or the direction of from where you have a compression, or where the compressive force is actually emanating from. So another hint in identifying reverse fault is you also have to take a look at the different deep pains. Sometimes it's very difficult to get the full picture at a glance, but what typically we do is to look at the different deep plane. For example, in this case, this is one deep plane, this is another one, this is yet another one, and then as you go to the right, there's a drastic change in deep plane and yet another one. So if I'm to rule a line, I'm going to just say I have this, this, and this. That tells me that there is first of all, I see asymmetry, but then secondly, it tells me that this whole bump is sitting on something else, which is actually an underlying fault. So looking at deep pain is actually another hint that tells you direction of movement, direction of deformation, and the possibility or the chance that you have an underlying fault. Another hint again at identifying reverse fault is difference in elevation with reference to let's say comparing the elevation of a particular strata to its position on the other side. So in this very case, this is what let's presume that this is called the base level. That's the original elevation of this particular rock strata A. What we see is that in the western part, it's actually been uplifted, and of course we know that naturally everything will preferentially remain in its flat position, except there's some form of deformation or some form of external force. In this very case, there is probably an external force that has pushed things and has made this layer to go from its original position to a newer elevation, which is up shallower. So in this very case, we actually look at the difference in elevation and say, okay, we have this unit and it's moved away from its base level, and that tells us there's some form of shortening, or at the same time some form of push or compression. And if that is true, that means potentially again we have an underlying fault here, which is in this very case called the reverse fault. Another hint that can help would be seismic fasces. Sometimes it's really not easy to see the whole element, but this is where you have to look at not just seismic fasces, but the like I mentioned earlier, the different deep panes and the different geometry. So in this case, I can imagine that I have one deep pane here, of course different fasces, and then I see that these fasces are different, but at the same time I also see that I have another deep pane here. Okay, and if I take another closer look, I see again that I have another set of deep pane here, of course different fasces also, and yet another one here. So if you put all this together, and I think I have some other different deep panes here, if you put all this together, it gives you a hint that between this area and this area, I might have a fault separating them. Okay, and between this area and this area, there might be another fault in this direction, and that's the way it goes. The question is, what are these faults doing? Because if I go into the deeper section, I see this set of deep panes, I see this other set of deep panes, so maybe the fault is going to come through the middle. I mean, the idea here is we're looking at not just the deep panes, but also the the reflector strength, reflector character, and based on that put potential discontinuities. Now this is a tentative or a possible interpretation for this area, and the message here is oftentimes it's not easy, or it's not so obvious when you look at sections like this on outcrop, on seismic sections, to figure out the fault. But you have to put together these elements: the seismic facies, the deep pains, and the behaviors, and you also have to check, overall elevations and decide. Like in this, for example, this package here is sitting right here. So what that tells us is that everything here has moved up, relative to what we have on this other section, because it's up. This whole package is up shallower than its equivalent on the other side. So based on that, you can actually interpret that you have a normal a reverse fault in this area. So that's just a bit of a hint on how some interpretations of some of this reverse fault mapping is done. This is an outcrop, and just something to mimic folded strata, and how you can go about putting some faults in the under whatever bump or anticline that we see. So let's, for example, focus for a moment on this layer. What we see is that, first of all, this is asymmetrical. Probably got some push in this direction, and so if we take this as the base elevation, we see that in this other part of it, it's actually shallower. Well, that's just an example, just an example of all that we've talked about. The idea here is you kind of have to figure out that, potentially we have a fault down here that is actually carrying the whole of this bump. So each bump has got a fault that is carrying it, and that's just a hint on how some reverse faults have been interpreted. So that's all we got to share for now. Thank you for following us, and please do send your message or send your comments if you have any. Until next time, please stay well.